Hello, gentlemen. Welcome to Chapter 13, entitled Properties of Solutions. In Chapters 10, 11, and 12, we talked about gases, liquids, and solids, and now we're going to talk about in Chapter 13, solutions, which are mixtures, specifically homogeneous mixtures that involve a solute and a solvent. We're going to be talking about aqueous solutions, which involve mostly ionic solutes and water or alcohols as solvents. 13.1 covers the solution process, with the major question of what does it take for a solution to form. So as a solution forms, a solvent pulls solute particles apart and surrounds or solvates them. When we're using water as a solvent, it's called hydration, or it becomes hydrated. Generally, we say solvates when we're talking about water or anything but as a solvent, but generally hydrate is what we say when we talk about water. For example, if an ionic salt is soluble in water, it is because the ion-dipole interactions are strong enough to overcome the lattice energy of a salt crystal. If you remember the crystallization or crystalline structure, it involves different particles like a cation and an anion together, and that's one unit cell, and another unit cell comes along and it stacks up in this crystalline structure. That is your ionic salt. But as a, let's say, polar molecule like water comes along with its partial negative and partial positive charges, this attraction here and here can start pulling apart this unit cell and isolating these ions. And that's how a solution can form. Now, there are three kinds of intermolecular attractions that are involved in the solution formation. The first one is solute-solute interactions. These are interactions that must be overcome, meaning the solute particles, for example, the ionic salt, the positive and negative charged ions, those have to separate. So you have that attraction has to be overcome. Second, the solvent-solvent interactions must be overcome, meaning the water molecules must break their hydrogen bonds and be separated from one another. So those cohesive forces must break. And then lastly, the solvent-solute interactions must occur. So not overcome, but must occur. So now we have loose solute, loose solvent, and the solvent and solute must interact together. And then we see the production of a solution. Each of these interactions stated above here involves some type of enthalpy change. Following diagrams. Here in blue, we have our solute crystals being very close together. Some energy here must be added, so it's an endothermic process to get these solute particles further apart from one another, breaking those interactive forces between them, or those attractive forces. In the same regards, here in the red, our solvent must have energy added to it in order to get its particles further apart from one another. Once these particles are far apart from one another, they can mix together, as we see here in delta H3, and that mixing process is exothermic. So when these particles come together, it's more favorable and it releases energy. So delta H3 here would be an exothermic process. And we see this in reality, these enthalpy changes, we see this when we make solutions. So earlier last semester, we made solutions. And we had a thermometer in our coffee cup calorimeters, and we saw some type of temperature change. Some temperatures increased, then we saw some overall temperature decreases. So we read it via temperature. But what's really happening is there's a battle being fought here. Not really fought, but there's a battle. Here, if we look down at these pictures here, this graph, and this left graph here, this is an exothermic solution formation. What that entails, well, what we feel is a release of heat. But what that entails is that my solute is broken apart here, and this delta H value is greater than 0. It takes energy to have that happen. And my solvent here, it takes energy to have that happen. That's recorded by this arrow here. It takes that much energy, and then that much energy. But when these particles come together here, they release energy. And if that release of energy is greater than the addition of energy to get them separated in the first place, it results in a negative delta H of solution. That's an endothermic solution formation. And the opposite is true in this picture to the right here. You have the separation of your solvent and the separation of your solute particles from one another, the individual solute to solute and solvent to solvent. If those enthalpies are greater than the overall exothermic process or exothermic enthalpy here for your mixing of the solvent and solute particles, then you have an endothermic reaction where your delta H of solution is greater than 0. This can be drawn up as the enthalpy change of your solution is equal to the sum of the enthalpy change, the enthalpy change of your solute added to the enthalpy change of your solvent added to the enthalpy change of when the solute and solvent mix together. If you add all these together, you get the delta H of solution. As I said before, the enthalpy required, or the energy required to get your solute particles to separate from one another is going to take energy. It's going to be a positive enthalpy. The same for your solvent. The delta H of your solvent is going to be positive because it's going to take energy. And then lastly, when you mix them together, it's going to be an exothermic process. Now we see this often when we make different solutions. So if I were to make a solution of magnesium sulfate, dissolve this in water, it would be an exothermic process. So my delta H of solution would be negative around 91.2 kilojoules per mole. That's exothermic here. So my temperature would read an increase in temperature. If I felt the beaker, if I felt the container it was in, it would feel hotter. And the opposite would be true for a substance like ammonium nitrate. The overall enthalpy of solution would be positive. So delta H of solution for ammonium nitrate would be around 26.4 kilojoules per mole. So this positive overall delta H of solution means that if I were to feel this container, it would be colder. So in this case, that means that this delta H of mixing was the largest. But in this case down here, this delta H of solution is positive. That means the addition of your solute and solvent enthalpies overpowered or was greater than the negative delta H when you mix the two solvent and solute particles together. Now all of this down here, this is the science behind hot and cold packs. You have a solute, magnesium sulfate, separated by a barrier with water on the other side. These two mix together and your delta H of solution is negative. That's a hot pack. In the opposite, you have ammonium sulfate on one side of a packet with the barrier separating it from water. You break that barrier when you smash it, giving you a cold pack, which is a positive enthalpy. So gentlemen, please take notes on this and come to class prepared to talk about these findings and expand upon this next class. Before we do, I'll leave you with a question. The question is, why do ionic solutes not dissolve in polar solvents? Come to class prepared with an answer. Adios, gentlemen.